Hello and welcome to Calculus tutorial. With this video we're going to take a look at the basic derivative rules. And so these are going to be sort of the bread and butter of the entire course. Not the only really important rules we're going to take a look at, but certainly the easiest and the most foundational. But because they are fairly simple, oftentimes to use them you do have to rewrite a function in order to take the derivative. And so we're going to look at a few ways to do that. And then, as always, trying to remember that with taking the derivative, you can still find the slope of a function at one point, which is the definition of the derivative, the slope of a function at one point. Alright, so to get us going, let's start with these basic derivative rules. So here they are. The first one, definitely the easiest, the constant rule. So if we take the derivative of a constant, so that's the derivative with respect to x of, say, the number 5. That is a constant. What would that be? The derivative of a constant is always 0. So if you think about that, if I think of the equation y equals 5, that is simply a horizontal line up here at 5. So I'm going to count up 1, 2, 3, 4, 5. You have your horizontal line, and because derivative is the same thing as slope, what is the slope of that line? 5. And that works for any constant, so any single number without a variable. Alright, linear. What if I take a linear equation? You might see how this is following sort of the same path as your Algebra 1 class. You start with constants, and you can go to linear. 10x minus 3 we'll do here. So if you have a linear equation, what is the derivative of that? Well, again, derivative means slope. So if I think of the equation 10x minus 3, hopefully you can sort of visualize that. 3 is your y-intercept, and then your rise and your run up 10 over 1 is like that. Well, that's the slope, remember? The 10 is our slope, and derivative means slope, so the 10 is our derivative. It's the slope. So that's fairly easy for constant or linear. But of course, this gets much more interesting as we start talking about curves, and that's when we first get to something interesting, the power rule. So what if I take the derivative of a power, like x to the 4th? What does that equal? And so I'm hoping you've recognized the pattern that we were looking at last week, is the power always goes down by 1. And so this is going to be an x to the 3rd. But what you do first is, it's not just a plain old x to the 3rd. The exponent, the 4, multiplies down in front. So it will become 4x, and because the power goes down 1, to the 3rd. That's going to be definitely our bread and butter for this course, is the power rule. The 4 multiplies down, and then you subtract 1 from the exponent. If I give you another one real quick, it's worth doing a few of these. If I do x to the 7th, what would that derivative be? Well, the 7 multiplies down in front, and then you subtract 1 from the power, which would give us 6. Alright, another important one is the constant multiple. This one I'm putting on here just to be precise and thorough, but you would probably do this one on your own most times without me putting a name to it, but mathematically it's still important for us to have a concrete example of how the rule works. So if I take the derivative with respect to x, I'm going to start with x to the fourth, but I'm going to put a constant in front of it, a coefficient, that is, of course, multiplying. Now, what would that do? I'm guessing most of us would come up with the correct answer, which is 20x to the third. Because yes, the 4 multiplies to the 5 to make 20, and then you subtract the exponent to get 1. Very similar to what you did up here. Technically, what you are doing is you are taking that 5 and factoring it out of the derivative. So you factored out the derivative, then you took the derivative, which is 4x to the third, and then you multiplied by 5 to get the 20. So it does become important with some problems that we can simply take that 5 out and in essence factor it out of a derivative. But for the most part, you will do that automatically. So if I give you one more quick example here, do this in green. If you were to take the derivative with respect to x of negative 2 sine of x, what would that equal? Well, the derivative of sine is cosine. We learned that last week. And the negative 2 multiplies that, and so the negative 2 just stays. So technically, what we did was factored the negative 2 out. So now it's on the outside of the derivative. Left inside is sine of x. And then hopefully you can see how we got to our answer. The derivative of sine is cosine, and the negative 2 tacks on there in front. All right, one more basic rule, and thankfully, again, this is something else that you would probably do even without me saying anything about it. It works out that nicely, and it's that intuitive. It's the addition-subtraction property, which basically allows us to do this with polynomials. So if I take the derivative with respect to x of something like 5x to the fourth, we'll keep that one that we're familiar with, but then I add some other stuff, so like a plus 3x squared minus 8x. So what does that become? Well, the addition-subtraction property allows you to take the derivative of each one of these terms individually. So the 5x to the fourth, take that derivative by itself. We know that gives us 20x to the third. 3x squared, take that derivative individually. So the 2 multiplies the 3, that gives us 6x. The 2 subtract a power, subtract 1 from it, and you get 1. And you could write a 1 here, but you don't have to. It's just 6x. And then the derivative of 8x, that is a linear term. And so it's just a number in front, which is 8. I'm guessing you probably could have gotten to that or assumed that was the correct answer from the beginning. There is technically a rule where addition and subtraction, you can simply take the derivative of each piece individually. All right, so those are our 5 basic rules. So let's erase this for us. So once you have the basic rules, you can start applying them in some slightly more complicated contexts. What I like to say is calculus is algebra on steroids. So the examples we had didn't require much algebra knowledge from your past, but the next ones will. So here are two examples. You can see they're a little bit more complicated, and we have to do an extra step before we can take the derivative for each one of them. So for the first one, it doesn't look like anything from any of our rules. So how do I take the derivative of it? Well, first we can rewrite this. And so I'm going to keep the 3 on top. I'm going to keep the 7 on the bottom. But the x I'm going to bring out of the denominator. And so we have to remember, how can you bring something out of a denominator? You make the exponent negative. Okay. So just a quick recap, x squared, or sorry, I might do x to the negative 2 power is the same as 1 over x squared. So a negative exponent puts something in the denominator. And if I want to undo that and go backwards and take something that's in the denominator and bring it back to the top, I simply add that negative back in. So my x to the 4th was in the denominator, and now it's not. So now I can take the derivative of this using my derivative rules. So what are they? Well, 3 over 7 is a constant, so it is going to stay. And I'll multiply that times the derivative of x to the negative 4. What's the derivative of x to the negative 4? Don't let that negative throw you off. You just use the power rule. So multiply by negative 4 times x, and then subtract 1 from the denominator. Now, careful here, this is a mistake that everybody makes. If I subtract 1, you do not get negative 3. You get negative 5. Negative 4 minus 1 is negative 5. But we can simplify this a little bit, I suppose. The 3 and the 4 can multiply to give us negative 12 over 7 times x to the negative 5. And now it becomes a matter of personal preference. You've got that negative exponent. Do you want to put it back down the bottom? You certainly can. Makes it look a little closer to what we started with. All right, so there is our derivative. One word of note, just remember these are primes because they are derivatives. This one is not. All right, one more here. As you can see, we have an x in the denominator again, and so that means we will be using the same idea as previously as using negative exponents, but we also have a cube root, which you haven't seen yet. It's also not one of the basic derivative rules, so how do we deal with it? Well, in algebra concept, a square root is the same as taking something to a 1/2 power. A cube root is the same as taking something to a 1/3 power. A 4th root is the same as taking something to a 4th power, and I'll let you continue that pattern on as long as you like. So I can rewrite this f of x. I'm not taking a derivative yet, so there's no prime. 6 over, and a cube root is going to be a 1/3 power. So that is the same as 6 over x to the 1/3. And now I'm going to use the strategy from example 1, that 1/3 power with the x is in the bottom. I don't want it to be in the bottom. So I'm going to bring it up to the top, but it has to be a negative exponent. Now I can take the derivative of this. So f prime of x. The 6 is a constant, it stays. Multiply that by negative 1/3. That negative 1/3 multiplies down with the power rule. You might be able to do some of this in your head. If not, I'm writing all the steps down for you. And then we have to subtract 1 from the exponent. All right, so we have to be a little careful here with our fractions. What is negative 1/3? I'll write it off here to the side. Minus 1. Well, remember we need a common denominator. 3/3. So we're subtracting off 3/3, which gives us negative 4/3. And if you would like to simplify that, 6 times negative 1/3 is negative 2. There we go. All right, one more thing that we would like to take a look at. Our last thing, we want to remember that derivatives can be thought of as the slope at one point. That's kind of where we started. And with all this talk about functions, we don't want to lose that fact. So how can we use these functions to actually find the slope at one point? So here's an equation. What is the slope of this function at x equals 2? So because I see the word slope, they want a slope. That tells me I want to take the derivative. Derivative means slope. It's a nice easy polynomial. The derivative of the first one is 2x. The derivative of the second one is negative 5. And the derivative of the third term, the plus 1, is 0. So I don't need to write it. So I want the slope when x is 2. Which is this point right here. What is that slope? Well, instead of using the slope formula, I can now simply plug in x equals 2 into my slope formula, my slope function. So if I plug it in, I'm going to write it this way, y prime at 2. Function notation kind of helps you see what you're doing. So plug that in, we get 4 minus 5 is negative 1. So my slope at that one point should be negative 1. And you might as well check it. Does this slope right here look like a slope of negative 1? Sure looks good to me. I hope it looks good to you as well. So if you want the slope at one point, you take the derivative as usual, and then you just plug in your x value, and that will give you the slope of your function at that particular point. Hopefully that helps.